Okay, so again, hopefully my voice will last. I have cough drops. But what we're going to do right now is finish talking about join optimization. We started talking about this last time. The important detail here is that it's very easy to have a massive number of potential join orderings if we have even a small number of tables. This was the expression given that a join is a binary operation between two tables, and if we have T1 and T2 and we join T1 to T2, it may be a different cost than joining T2 to T1. So because of that, we have a very large number of potential combinations and arrangements to consider, and this is the expression for that. Last lecture slide had a reference if you wanted to go see how this was derived. But we had this number of potential join orderings that you could end up with. 5 tables, which is not uncommon in SQL, to have nearly 1,700 possible orderings to consider. So this is not really feasible or practical when you're considering plan generation. And so a lot of databases constrain themselves to just left deep join ordering. Not all of them do. And it's interesting because sometimes when people do NanoDB projects, they modify their planners to consider any possible join ordering because they use a materialized node and they plop that in, and that allows them to do, for example, nested loop join. But this is nice because it allows us to have a greatly reduced number of potential orderings to consider. Like I say here, n tables. Only will have n factorial orderings. So that's nice. And left deep just means that we join the left two most first, and then we join the third one in and the fourth one in. And that's actually the way that we parse them as well. So if you don't use parentheses in your A join B join C join D stuff, then you're probably going to end up with that anyway. Now, we talked about the bottom-up join optimizer. We'll go through this a little bit more quickly, but this was just basically a way of generating an optimal join order from a set of input tables. So you take all the tables that are going to be joined, you kind of put them in a big bag together, and you start making passes over them. And the first pass is try to figure out the fastest way to access each thing by itself. So I look at table T, and I have a predicate that says T.A greater than 5. And I say, oh, I can apply that predicate when I do a file scan over that table. So I generate that little plan fragment, figure out how much it costs. T2, oh, I don't have any predicates for T2. I'll just stuff that there, do a file scan, and so forth. You do that. And then what you do is you make a second pass, and you figure out how to join one more table into each thing that you have. So like it says here, you consider every pair of relations that could be joined, or every pair of tables. And you use the cost that you computed in step 1 to figure out what's the best way to compute the join of this pair of things. So if you have these two things, then you say, well, is it better to join them this way, or reverse the order and join them that way? What join algorithm should I use? You figure out the best thing you can do, and then again, you compute the cost and you save it away. And you repeat this process each time, adding one more table into the process until, so in step 3 you would generate all optimal ways of joining triples of tables from your input set. And you finally get to the point where you have one optimal way of joining everything together. Pretty straightforward approach. It's dynamic programming, and it definitely works. You get a nice optimal way of doing it. The only issue is that it's greedy, and as we'll talk about it, this can actually cut off certain optimal approaches that we might otherwise want to use. Yes, question? How long does this process take? Okay, that is a very good question. I don't actually know off the top of my head the time complexity of this. Anybody know off the top of their heads? I'd have to think about it, and I'm kind of really lazy right now, being sick again, to figure out the time complexity. Yeah, I'm too lazy to think about it anymore. I will get back to you. Yes. So interestingly enough, conditions also all go into a big bag. And what you can do is you can do sort of a constant time lookup on that bag to say, hey, what references stuff from this schema or that schema? And then you just pull out the conjuncts that apply to each thing that you're looking at. No. That's a very good point, and that's kind of what this thing tries to do, because in each one of these steps where you try to figure out what's the lowest cost way of joining pairs of tables, somewhere in there you would see the pair of tables that only generated one row. And then probably what you would end up is when you do the next level, you want to join that pair of tables that only produces one row to something else that also will only produce a small number of rows. So basically what happens is all the way up the process, the least costly option in all of the options that you're considering tends to be stuff that generates the fewest rows, generates the fewest IOs. And so what happens at the top is you end up with the plan that maybe in a global sense generates the fewest rows and does the fewest IOs. That ends up being the lowest cost. So what you're saying, I think, is absolutely correct. But the question is, what's the time complexity of this algorithm? And that one I don't know off the top of my head. Okay, I can tell my voice is going to barely make it. Now, there's another approach which is given in the database textbook, which we don't really talk about anymore, but there it is, Database System Concepts. It's the Silberschatz book. And if you happen to track it down, that's perfectly fine. I have one. It's a nice reference, but I'm kind of beyond the material in there by now. Of course, I've been teaching this stuff for like 7, 8, 9, 10 years, so of course. But here's the algorithm that they have in there. So find the best plan. You have some set of tables, or in their parlance, a set of relations that you want to join. And you basically go into your collection of plans, and you say if you already have a plan that joins all of the tables in S, then the cost won't be infinity. That's your placeholder to say, I don't know what the cost yet is. You just say it's infinity. If you have a non-infinite cost, you say, well, I already have the optimal plan for this thing. I'll just return that. So this is sort of the memoizing aspect of this algorithm. Now, if S contains only one relation, well, then we do what we had before in the bottom-up approach. We try to figure out the optimal way of accessing that one table. Otherwise, we might have a situation where we have multiple tables being joined, and we need to figure out the best way of doing that. And so you see this rather complicated way of doing it. We set best plan S's cost at infinity, which presumably it already had to be, because we had if best plan S cost is not infinity up above. I don't know why they would have that. But anyway, go through here. That would obviously be an initialization phase that occurs beforehand. For each non-empty proper subset, S1 of S, so we go through and we look at all the subsets of this set of tables. And then we take those subsets and we figure out what's the best plan for joining that subset. You can see that this is kind of an expensive approach, which is why generally people prefer the bottom-up approach. So P1 is find the best plan for the left subset, and then P2 is the right subset, so S minus S1. And then you figure out the best join algorithm and all of that malarkey. Do I have indexes to use? You could use that to try to improve the join costs and so forth. You figure out the cost, and this may not be exactly the cost, so that cost equals P1.cost plus P2.cost plus cost of A may not actually be accurate, because it may be, for example, if we're using nested loop joins, that it's going to be something like the left plan's number of rows times the right plan's cost, because we have to traverse the right subplan multiple times. So just, there's some suspension of disbelief in the statement of this algorithm. And once we figured out the cost of joining S1 and S minus S1, we say, that's the cost, and if it's better than what we already have, we'll replace the current thing with the new thing. And then you just keep repeating this, and you can see that eventually you will have the optimal way of joining S. It takes a while to get there. It's expensive to get there in this approach, which is another reason I don't like it. But at the end, you have the optimal cost plan. You return it, and then next time you come in here, we can just look it up. We already have it. In fact, we'll already have all the optimal plan costs and plans for all the subsets of S as well, because we'll have already looked at all of them. Everybody see how this works? Again, I don't like it, but it's out there. The other thing is that obviously when you're using this in your planner, you just go in and you say, find best plan, all my tables, and off you go. Out pops the right thing. And again, it's memoizing as it goes. Alrighty, let's see. Yeah, return the best plan. That's the best part. So this is hard to constrain to do left deep subtrees, or I should say left deep join plans. It is possible. It's a little bit grungy. You have to take the innards of it and adjust it a little bit when you're. It's in that section where you're saying, well, I want to generate all the proper subsets of this set of tables. You have to think a little bit more carefully when you're doing that. But it's not too hard. You can still do it. And that way it would just do left deep. But there's a lot of other costs as well, like generating these subsets every step through this algorithm is just kind of really annoying. And so that's why I like the bottom-up approach. I feel like from a resource usage perspective, it's a lot more efficient. It uses memory better and it uses less computation. Okay, so that's the top-down join optimizer. And the thing that I was mentioning before is that this is a greedy approach because each time we take a step and we say, what's the cheapest or the best way of doing this? But that may actually cut us off from optimizations further along. And so there's another approach which is very widely used called Selinger style optimization or Selinger optimization. And basically what Selinger optimization does is it keeps some non-optimal plans around because they may become useful later on. And what defines a non-optimal plan as possibly being useful is that it orders its results in some way. Because there's certain benefits that we can get from ordered results. We may be able to do grouping and aggregation more efficiently. We may be able to do duplicate elimination more efficiently. We may be able to do equijoins more efficiently. So if we have the ability to save some of those non-optimal plans, we may find that they actually give us a huge benefit higher up in our plan generation. So there's a lot of reason to keep them around. Now, you may say, who's this Selinger person? Why do we care what Selinger says? And the reason why is because this person, Pamela Selinger, actually was working on the SystemR database, which if you are interested at all in database systems, you should go and read about SystemR because this is a very important research project for the world of database systems. A lot of what we do is based on what was achieved in SystemR. And so, like I said, most database systems use Selinger optimization, and so it's nice to know where it came from. So yeah, early relational database research project at IBM. This is where SQL came from. The predecessor to SQL was SEQ. So there is a U in there. SEQUEL. There actually turns out to be a quell language as well, QUEL, query language. And so SystemR introduced SQL. It introduced the notion of doing this join ordering thing, keeping around non-optimal plans so that they may actually be able to help Selinger optimization. And also transaction processing. SystemR incorporated transaction processing. Because it's funny, every time these things come up, everybody's convinced there's no way we can use this in a real system because it's going to be way too slow. Same thing with some of the early compression algorithms. They thought, this is a great compression algorithm, but there's no way we can ever implement it because our hardware is not capable of doing it. And like those are the old school compression algorithms that aren't very good now compared to what we have. So it's just, the advance of technology. But SystemR is a really important project. Now, the way that SystemR's optimizer worked is, like I said, just a little tweak to the way that our bottom-up optimizer works. We do the same thing. We go through all of our individual tables that we're looking at, and we figure out the optimal plan that would generate results. But we also figure out plans that would I'm sorry, I have this back. Yeah, so we also keep around plans that would generate ordered results. I wrote this backwards compared to the way I just explained it. So we have the optimal plan that produces no particular order, and then we also keep around plans that produce specific orders. And of course, we may have a situation where we don't need to keep around the unordered plans result because we already have an ordered plan that's cheaper. Let's say we have a sequential file, and we can just scan through it and it's automatically in order. There's no reason to keep an unordered version around. So we have this. And yeah, so this is what I was saying. Step one, for each relation, we look at the indexes to see what result orderings are available, and we generate results based on those things. So each possible result ordering, we generate a plan for accessing the relation, applying whatever predicates we can as well. And we also generate a plan for unordered access, and if that's already more costly than something else we have, then we throw it away. So that's our first level. Now we know how to access each thing, but we also have some details about how to access things in interesting orders. Step 2 does the same thing. You again go through and enumerate all possible plans for joining pairs of tables. But instead of just looking at plans that generate unordered results, we also keep around plans that generate interesting ordered results. And so what's described here now is when we have all of these plans, and some generate them in orders, some generate them in no particular order, we group them based on the ordering of the results. So all the plans that generate unordered results would go into one bucket, but then we just pick the optimal unordered result plan. So the plan that's the cheapest that generates unordered results. And then we have plans that generate results in some particular order, and we might have a few plans there. And we just pick the one that's most optimal for that ordering. And we do that for all the orderings that we could possibly generate from the inputs. And so you go ahead and continue doing this up. You know, the next phase, you join 3 tables together, and some results are unordered, some are ordered. We group them by whether they order or not, and by what they order, and we pick the optimal plan for each ordering. And we just continue that all the way up until we have some set of plans. All the plans at the top level will join all n tables. But some will have ordered results and some will not have ordered results. And then we can just choose one based on what else we have to do in the plan. If we have no order by and we have no group by or duplicate elimination, we just pick the cheapest one. We don't care about the ordering. But if we have a situation where we have a group by or we have an order by or a duplicate elimination, we could pick a plan carefully, seeing if there's an ordered result plan that might help us do these other things more efficiently. So that's the basic idea behind Selinger optimization, is we try to keep around plans with interesting orders that we can take advantage of. Okay? Make sense? All right. That's that. Now, thankfully, this does not greatly increase the memory overhead of plan optimization. The one thing about this is that it will increase the complexity of your data structures, because you also have to think about what are the orders of the results of my various subplans. So you now have to use that as part of your indexing mechanism in your data structures. But the reality is that most tables don't have very many indexes. We might have a few indexes for primary keys, foreign keys, and then if people add other indexes to improve plan execution or query evaluation in certain circumstances, well, then they expect us to take advantage of them. And that just sort of automatically falls out of this approach, which is really nice. And so you have a few indexes that will increase the amount of memory required for this planning by a little bit, but it doesn't increase it by a whole lot. Yes, and let me see, yeah. And so the nice thing about this is that we can, there's a lot of situations where we can take advantage of this higher up in the plan. You know, and a situation like I was describing before, where you might have a predicate on one table and a join between 2 tables, and you have an index on the predicate and an index on the join attribute. Well, Selinger optimization can figure out which index should be used very easily. Our naive approach of pushing down predicates always as far as they can go may not allow us to do an optimal plan evaluation, but Selinger optimization would handle that very, very easily. So that's kind of a nice thing. Okay, and so any questions about planning? I would have loved to spend some more time talking about doing nested query optimization, but like I said, I was sick over the weekend, had no energy to put together a lecture on that. So there may still be one in the future. I'm not going to write it off, because if I do, then I'll be able to incorporate it next time I teach the class. But that's basically all we're going to talk about with optimization, at least as far as you'll require for the fourth assignment. You don't need anything beyond this for the fourth assignment. Okay? So what we're going to do now, at least for the next half hour or so, is talk about indexes, and then we'll take a break and then pick it up in a week or so. Indexes are something that we're all generally very familiar with because we all have had to use them at this point. Indexes are a very helpful mechanism because most of our queries don't actually need all the rows in a table. We might have that if we have grouping and aggregation, something like that. But in general, we are frequently looking up a small number of records that we care about. Same thing with joins. When you're joining things together, I may have one table and I'm looking at the records in another table that might join against this record, and I would like some way of retrieving just those records. So again, I'm trying to identify a few records based on some records values. And we have only used file scans because we don't know anything better yet, and it is slow. You'll start to see that on the third and fourth assignments when you have a few queries that you can write that will take a while to evaluate just because we only have simple tools and no indexes. But indexing is a very, very common technique for making this kind of thing a lot faster. So we're going to start talking about the concepts behind indexes, and then we'll start getting into various implementations of indexes in a week or so. So indexes, the important thing to remember about indexes is that they are separate from the table data that we want to actually access. So that's why we call them an alternate access path, because they are a separate way besides looking in the file itself for finding particular rows in the file. It's just like everybody's seen books. At the back of the book, they have an index. The index is part of the book, but it's separate from the text. And you have two choices. You can either look in the index and find references to what you're looking for, and then go look in the book, or you can search through the book page by page to try to find the material that you're looking for. Okay? One is much faster than the other, and you hope that the term that you're looking for is in the index. Now, indexes have what we call a search key. The search key is basically how we identify records using the index on the table that the index is built against. So like it says here, there'll be one or more attributes that are part of the search key. And it's important because this is another term that has the word key in it. This is different from our primary keys, our foreign keys, and so forth. Just make sure that you keep that in mind. Search keys are just what indexes use to look things up. Are search keys even required to be unique? Well, they probably would be on an index that's built on a primary key column. But if it's built on a foreign key column, there's not going to be unique values in there. There's going to be duplicates probably. So search keys, similar concept, but they're not really that identical to candidate keys and so forth. And of course, tables can have multiple indexes, and each index has its own search key. You may also have a situation where you have two indexes on the same search key, but using different index formats. Uncommon, but you can certainly have that as well. So, like I say here, there's different kinds of indexes. I'm hoping to talk about both sequential indexes and hashing indexes and give you a couple of hash file formats that are really interesting because they change dynamically over time based on your data distributions. But you can see access patterns, access time. So what kind of lookups do my indexes support? And remember, we really like sequential indexes or ordered indexes because it allows us to do range queries as well as doing lookups really efficiently. And so there'll be various kinds of access that are efficient. It'll be various time complexities for looking things up. Indexes, of course, have to be kept in sync with their tables that they are built against. So we have to say, how much time does it take to modify this index? How much time does it take to delete a record from the index? And also you have to think about the space requirements of indexes. Indexes are nice because you build them on a subset of the columns in the table, usually. But the problem is that that is going to still take up some space, especially because the indexing structure may require additional space. We talked about B-trees, and we're going to introduce B-trees today. B-trees nodes can have up to 50% empty space. So imagine how much ever space your index data takes up. It could be twice that for the index itself. It probably won't be, but it could be. So you have to think about that kind of stuff. And like I say here, typically space is cheaper than time, and so the cost of the space is usually far outweighed by the amount of time you get to save, because maybe customers will actually use your product because it's efficient to them, and so forth. So categories of indexes, we've already talked about this some, but you have ordered indexes and you have hashing indexes. So ordered indexes maintain their index entries in order of search key. And so generally, lookups, deletions, those kind of things, additions are all log time. And you can do range queries, which is really, really nice. Typically, the way these things are designed is you use a lookup to find the record entry, and then you can traverse linearly from that point to traverse the entire range. So that's kind of the nice thing about ordered indexes. Hash indexes use some kind of hash function to distribute the values. So you use a hash on the search key to figure out where to start looking. And it's generally constant time. With some of our indexing structures, we actually achieve constant time. If we do static indexing or static hashing, then we don't have any guarantees it'll be constant time. So that's the only problem. And you can see that hash indexes don't give us any benefit for range queries. So that's fine. We probably just wouldn't choose to use them in that situation, because we'd have to scan the entire file anyway. Okay, so sequential files stored in search key order. One thing that's interesting about sequential files, what we're talking about is the table file. We're saying the table file is sequential. And so far, I've been watching people, they insert data into their database, and they select it out, and it comes back in whatever order, probably the order that you inserted it. Sometimes that's not the case, and it's always interesting to try to figure out why. But in general, sequential files, when you insert the data, it puts the data in a place so that the records are always in some order. So we're not actually talking about a sequential index. And what's interesting about that is that it's still helpful to know, or it still may be helpful to build an index on that sequential file, because it allows us to stop looking for certain records in certain situations. Like I say, you might have a situation where the index entry is much smaller than the table record itself, so it's a lot more efficient to do an index lookup on the table. Let me see if I have any more details about this. See, unfortunately, who here has actually used a paper encyclopedia ever in their lives? Like a few people? Really, who hasn't? I want to see a show of hands. It's not like something to be ashamed of. It's just times are changing. Yeah, see, that's the thing that's really wild to me, because I grew up in high school writing papers out of encyclopedias. It's like we didn't have Wikipedia, we didn't have the internet. I could have used Gopher, I suppose, to get on what was the internet at the time and look things up. But encyclopedias are exactly this kind of layout, because each encyclopedia book has articles in it, and the articles are in order by topic, alphabetical order by topic. But the entire volume of the encyclopedia is made up of all of these individual books, and on the spine of each book it would have letters, like this is A through AE, and then the next one is AF through B, or BA or something like that. And so basically, the spines of the volumes in the encyclopedia were an index that you could use to look into the specific encyclopedia volume you needed to look at for the particular article you were curious in. So even though the encyclopedia was in sequential order, it was efficient to have that indexing mechanism built into the way the books work. And unfortunately, a lot of people can't really relate to that anymore, because we don't use it very much anymore. So that's this whole notion of primary indexes. Primary indexes are indexes built on sequential files using the same search key that the sequential file uses, which is very interesting. Now, one question. If I have a primary index, does it have to have every single record from the file that it's built on? So we're introducing another concept. Does the index have to be dense, or can it be sparse? If you think about the encyclopedia example, it certainly does not have on the spine a list of every topic in that encyclopedia volume. It just says these are the letters of the articles at the beginning of this encyclopedia volume, all the way to the end. So in our encyclopedia example, that is actually a sparse index. Why is that? Well, because I want to look up, let's see, let me think of something that would be good to look up. Berbers, I don't know. So you go and say, I want to look up Berbers. And so you find the encyclopedia volume that will contain that, and then what do? You start flipping through the pages until you find Berbers. And so that's the same way that these primary indexes can work if they're sparse. They tell us where to slot into our sequential file, and then we can start searching from there for the actual thing that we need. So that's why these primary indexes are able to be sparse. Okay, so yeah, like it says here, sequential file plus primary index, that has a name as well, index sequential file. We have a sequential order, but then we can use our index to hop into it in the appropriate place to try to find the thing that we're looking for. And so this is what I was saying before. Dense indexes will actually have an entry in the index for every record in the file that they are indexing. And so that makes it very easy to get to exactly the record that we need, but the index is then large because we have to keep track of every record. So if we have a very large table that we're indexing, and it happens to be in the same order as our index search key, in that case, we can use a sparse index and only keep entries for a subset of the records. Let's say every 10th record, we could keep an entry in the index so that when we use the index to look into the sequential file, we plop into a place that we know is near, but is not necessarily the record that we're looking for. So we have to search till we find it. And then there we go. We're done. So this is the difference between dense indexes and sparse indexes. So that's primary indexes. Remember, primary indexes, same order as the file that they index. Secondary indexes are 99% of the indexes you will ever create because they are not in the same search key order as the file they index. Now, since our secondary indexes tend to be B-tree indexes and our files that we're indexing tend to be hash files, heap files, I always get those mixed up. They're almost always in different orders. So in that situation, all of our indexes that we build in most of our database systems are secondary indexes. They're in a different order. In this situation, the index has to be dense because if it's not, it may simply not be possible to look for certain records without scanning the entire file. Okay, does that make sense to everybody? So if it's in the same order as the file that we're indexing, it's a primary index. If it's in a different order, it's a secondary index. Primary indexes require some organization of the file that's being indexed. Now that said, you could still have a file that's in one order and a secondary index built that's in a different order if you had various queries that you wanted to support. But since we always have heap files and they're in no particular order, all of our indexes are secondary indexes. Now, B-trees are the most common indexing structure that we use, and B-trees are interesting. It's actually a whole family of tree data structures used for files. And so we're not going to talk about all the variants because there's like B-star trees, and there's B trees, and there's B-plus trees, and there's a few other ones as well. But we're not going to talk about them all. But these support both direct access and sequential access. Direct access as far as the search key is concerned. And the tree's depth does grow automatically. The nice thing about it is it does stay balanced in general. So actually, well, B-plus trees stay balanced. And that is a great benefit because we know what the cost will be to look things up, and we can use that in our calculations. The space within a block is managed automatically. All of the nodes are expected to be at least half full. There's only one situation where a node is allowed to be less than half full, and that's if you only have a root node and you don't have enough data to make it at least half full. So that's the one situation. And like I say, it's usually you don't need to worry about overflow, although you may still have a situation where an individual record in a page overflows, and then you would have to have some special support for that. The branching factor on these indexes, or these B-tree data structures, I should really be more general, tends to be very, very large. So typically your index entries are small. They're on the order of 4 to 12 bytes maybe. And if you have a B-tree node that is 4 kilobytes or 8 kilobytes, you can see you can fit a lot of entries into each node. which means that the tree is very flat and is very broad, which is really nice because we do one lookup per level in the tree. And if our tree only has 4 levels and we can index 1 billion records with 4 levels, I have 4 IOs to look up the record I want from 1 billion record file. That is way better than scanning through it. So we love B-trees. Now this is just a little bit of trivia. It is unclear what B-tree stands for. It definitely does not stand for binary because these are not binary trees. But various things have been suggested over time, balanced, broad, bushy trees. I don't know. I couldn't even guess what the B stands for. I can't even offer a suggestion as to my favorite one because I really don't know. And like I say here, I don't really care either. Just call them B trees. But yeah, it may actually. I mean, even the whole like developed by Baird. I mean, the other guy that helped develop them didn't have a B in his name, so it's like no idea what the B stands for. But the various. Like I said, B trees are a family of data structures, and they have different constraints on how the data is managed, whether you have indexing and data mixed together, whether you have nodes that are half full, or 2/3 full, or 1/3 full, all of this kind of stuff. This is where the variations occur. And if you're curious, I can point you at books that talk about the variations in a lot of detail. There's some old books from like the 70s that actually go through this stuff. Sadly, you don't see a lot of coverage of this material anymore. But the most widely used one is the B plus tree. And so that's the thing. Like anytime I say B tree, I usually mean B plus tree. If you're talking in an interview with somebody about database systems and they say B trees, they probably mean B plus trees. And certainly in a lot of literature, they also mean B plus trees. The reason why we like B plus trees for database systems is they actually separate the indexing portion and the data portion of the file format. And this is why it's both a benefit and a drawback. We have inner nodes and we have leaf nodes. So we have non-leaf nodes and leaf nodes. And leaf nodes are where all the important stuff is. That contains our data records. All the inner nodes provide indexing structure that get us to the leaf nodes that we care about. So like I say, your internal nodes have different structure than leaf nodes, which is fine. Internal nodes only store keys, which is kind of interesting. There's some caveats about that, which you'll run into when we get to the B-tree lab. But also, the leaf nodes store keys and data. So that generally is how we lay this out. And B plus trees can be used for storing sequential data files, like tuple files, as well as indexes. And that's one thing that NanoDB, that's part of the reason why NanoDB was laying on the operating table with its chest open for like the last 9 months, because I was actually making that change to the database system internally. That now you can use the B plus tree format for tuple files as well as for index files, which is really neat because you can actually say create table blah blah blah, and you can put this properties clause at the end, which I mentioned in the second assignment, and put in like storage equals B tree or something. I can't remember exactly how you say it. You can't do it right now because you don't have the B tree implementation, but you will be able to do that in the future, and it allows you to create tuple files that are sequential as well as heap tuple files. That will be in the 5th assignment. Yeah. And the problem is, I don't give you the full working implementation of B-trees because I want you to learn B-trees. And you may screw it up. So if you do, we'll give you code for that. But thankfully, nothing else requires B-trees to work. So if you completely screw up B-trees, it won't end your life. Because the 2 assignments after that are transaction processing and concurrency control. They don't actually care about B-trees. But you may want to have working code for other things, like what I'm hoping is after the official assignments of 122, we'll have some very flexible assignments where you can work on things. That's if we have time. And I have some things that I think would be really helpful, A, for the class in the future, and B, would be interesting to implement. And if you want to do indexing stuff in CS123, obviously you'll have full access to the code base at that point, so that'll be no problem. Okay, let's see. Yeah, so these are the other details. Again, we say nodes have to be at least 50% full. Why do we say that? Because other B-tree variants don't require that necessarily. There's some that require at least 33% full, some require at least 66% full. It really varies. And so the B plus tree says at least 50%. Every path from the root to the leaf is the same length. We like that as well because it allows us to do very efficient costing, and I should say accurate costing. And key values may be repeated in different tree nodes, which is another one of these interesting things. As we go from root to leaf, we may see the same key value multiple times. The original B tree format didn't allow that. And the reason why is it was mixing records and indexing, which was unappealing. Another place that you frequently see B plus trees, which is unusual, is you see them in file systems as well. Because if you think about it, if I seek, you guys have been, working with code that does this. I want to load page 53. Well, think about what the file system is doing. You say, I want to access data at this logical offset. Page 53 times 8 kilobyte page size gives you an offset. But that doesn't tell you what disk sector. And so the operating system has to translate that logical offset into the disk sector on the actual platter where the data is stored. So B plus trees are frequently used for that indexing mechanism into files. NTFS uses B trees. And Linux doesn't use B trees. I'm trying to think what else uses B trees. But there's a few operating systems that do. Okay, tree nodes have up to n children. We're going to simplify in our discussion that n is fixed. But in the actual NanoDB implementation, n can vary from node to node. Obviously, keys can be varying size and so forth. So it really can vary. And this is the internal format of a B-tree node, where you notice that we have pointers interspersed with keys. We have n pointers and n-1 keys. So we have a pointer and key sandwich here. And basically, the keys are kept in sorted order. So K1 is less than or equal to K2, is less than or equal to K3, and so forth. And like I say here, in the case of duplicate keys, you'll have a range of duplicate key values. For indexing, though, we have a constraint that the keys actually have to be unique. And we'll talk about how we make that happen in the future. But if we did have equal keys, then they would just form a range. Okay, for leaf nodes, the pointer points to a record that has that key's value. So P1 points to a record with K1's search key value. P2 points to a record with K2's search key value, and so forth. So this is how we index into the table file. We have pointers into the table file, and we have the key that goes with that pointer. And of course, if we have our search key built on a primary key, then we're really happy because we only have to reference one record. And all of our key values would be distinct. But we might have a situation where the search key is not a candidate key, in which case we may have choices as to how we implement this. We could either have K1 have a collection of P1 through whatever, PI, that are the records with that search key value, or we may just have K1 P1, K1 P2, K1 P3, and so forth. So we just repeat the key values. Okay. So those are our two options. We can either have sort of collections of values associated with each search key, or we could have just a range of records that are repeated key values. NanoDB does the repeated key values because it turns out that it's actually quite preferable to do it that way. And again, we'll get into some of those details on the assignment. Okay, leaf node. So Pn points to the next leaf in the sequence. So Pn will point to a leaf node whose K1 is greater than or equal to this node's Kn-1. So that we have all the records in sequential order. And so, yes, the leaves contain non-overlapping ranges of key record associations. And so what this allows is we can use our indexing structure to drop into our leaf nodes at the appropriate point and then scan forward with things in increasing search keyword. So that's how B plus trees are able to do these range queries so efficiently. Okay, non-leaf nodes are a little bit more complicated because they represent the internal structure of the B tree file. So if you thought that setting values to be null or non-null was annoying, just wait till you have non-leaf nodes with pointers and suddenly you have a cycle in your B tree and you don't know why. Or it points to La La Land, which is a favorite place for computer programs to go. So you have to start being a little bit more careful because now we have a tree structure that we're representing in the data file. Now these pointers, like I say here, P sub I points to a part of the B tree structure with key values that are at least K sub I. But they're less than K sub I. Do I have that right? Pointer, oh yeah, 1 through, oh yeah, so let me see. Oh, so this is like P2 through Pn minus 1. That's right, okay. So Pi points to a subtree containing search values of at least Ki minus 1. That's right. So the key is sandwiched between two pointers. And the left pointer points to stuff that's at least K, the key's value. The right pointer will point to stuff that's larger than the key's value. So again, you can see how it allows us to chop down our set of data based on the key values that are interspersed. So for I equals 1, that's going to point to stuff that's less than K1. So it's all the stuff that's less than K1, and Pn points to stuff that's at least Kn minus 1. So that's how we do this. I have a pointer. The key to the left says it's at least this pointer, it's at least this key's value. To the right, it's less than that key's value. So each set of keys, each pair of keys gives the range of the data pointed to by that pointer. So yeah, this is another way of thinking about it. P1 points to the subtree with search keys in the range minus infinity to K1. Now, that said, of course, there may be a left sibling to this non-leaf node that also has a constraint imposed. So we could actually increase the minus infinity bound and decrease the plus infinity bound. But at least for a leaf node considered in absence of any other parts of the tree. And so forth. So you can see how the P2 points to subtree with search keys in the range K1 inclusive and K2 exclusive, and so forth. Here's a very simple B plus tree. And this is going to be the last thing that we look at today. So you can see, for example, this was just built on the branch names. If I wanted to look up Redwood, you can see that Redwood appears in multiple places. Perry Ridge appears in multiple places, and so forth. So we would, if we were doing this, we would say, I want to look up Round Hill, and you would look at the first thing and say, well, Round Hill is larger than Perry Ridge. I need to follow the right pointer. Round Hill is greater than Redwood, so I follow the right pointer, and I end up in this leaf, and I linearly scan through, or I could binary search because the records are in search key order, and find Round Hill. If I want to find downtown, well, it's the same thing. It would be less. I'm trying to think of a good one. Yeah, Perry Ridge would be a good one. It's equal, so I follow the right pointer. And I go to Redwood, and Perry Ridge is less than Redwood, so I follow the left pointer, and I end up in the node with Perry Ridge. So forth. Okay? Any questions? Okay, so like I said, that's all we'll talk about for now. And next time we get to, next time we have class, we'll start getting into a lot of the details. How do we modify this data structure? How do we add records to it? And worse, how do we delete records? Because you can see that as I add stuff, I need to start splitting nodes. And when I delete stuff, I have to combine nodes, which is neat because it means the data structure will shrink and grow based on my needs, but it also means I have to shuffle data around, and that's what makes it a little bit complicated. So we'll get into all of that in about a week. We'll start diving into that complexity.